So welcome to lesson 4 on refraction, refraction part 1 from light and sound. And in this lesson, we're going to look at part 1, which are the laws of refraction. So go to your notes, because I want you to do these questions with me. And let's look at the laws of refraction. So let's say I have this situation here. This represents a container with two different liquids. Let's say that's water, where waves travel faster. And let's say this is something like oil, where waves travel a little bit more slowly. This is more viscous. So I'm going to have a wave, which I'm going to generate here. I'm going to generate using an oscillator, something that moves up and down in the water. And when it moves up and down, the waves will travel out through the water as shown. Now that particular wave has a certain speed in the first medium. We call that speed v for velocity. We call that speed v1. And it's also got a certain wavelength. The wavelength will be the distance from crest to crest. We'll call that wavelength lambda for wavelength, lambda 1. Then it's going to move into a medium where the wave slows down, something like oil. And as a result of that, the wave slows down. And if you like, the waves kind of stack up like this. So its speed is now v2. v1 is greater than v2. And as you can see, when the wave slows down, the distance from crest to crest, lambda 2, gets smaller. So lambda 1 is greater than lambda 2 in this particular instance. This is what refraction is all about. Refraction is something where waves will change direction when their speed changes. Reflection was about waves bouncing back, and refraction is about waves passing from one medium into another medium. Let's have a look at this diagram here. Let's say I've got the same situation again. So there's medium 1, which is a faster medium, and here's medium 2, which is a slower medium. This time I'm going to have my wave here, which I call my incident wave, and it's going to go in at a certain angle. You know, it might be easier to draw my wave just as a straight line. So instead of having my wave like that, we often represent the wave as a straight line like that. That's my incident wave. And that incident wave will make an angle of incidence with the normal. So there's my angle of incidence, I, in here. What happens then as that wave travels into a slower medium? Well, when it slows down, it actually bends. It's going to bend towards the normal. So it's got a speed v1 here. It's got a wavelength lambda 1. And then when it slows down, it bends. And the wavelength gets smaller. Again, you can represent this wave. We'll call this wave here the refracted wave. So here's my refracted wave. The angle the refracted wave makes with the normal is called or, the angle of refraction. But don't mix that up with or in the previous lesson, where or was called the angle of reflection. It's all about context here. The speed here has changed to v2, and the wavelength has changed to lambda 2. So the speed is slower because it's moving in a slower medium. Now back to this diagram here. One thing you should note, and it's really important, is that, okay, when I moved into the second medium, it slowed down. So v2 changed, and also lambda 2 changed. So its speed and its wavelength changed. But I tell you what does not change. The frequency f does not change. You see, the frequency of the wave, which is the number of waves per second, that comes from the oscillator. So if the oscillator bops up and down 10 times per second, you'll generate 10 waves per second. And then when those waves travel into the slower medium, you don't lose waves. You still have your 10 waves per second. So the frequency does not change from one medium to the other. The velocity changes and the wavelength changes. Now, the person who did a lot of work with this was somebody called Snell. So let's go back to our notes for a minute. First of all, you have your definition of refraction. So here's my definition of refraction. It's the changing of direction of a wave when it enters a region where its speed changes. That's what we call refraction. So its direction changes when it enters a medium where its speed changes. Now, someone called Snell did a lot of work on this, and Snell came up with a lovely little formula. We want a formula that shows the relationship between the angle of incidence and the angle of refraction. When we did mirrors, it was a dead easy relationship. I was equal to R. But here, it's a more complicated relationship. And Snell came up with a law called Snell's law. So let me examine that in a little bit more detail. What did Snell discover through experiment? He discovered that if he found the sine of the angle of incidence and he divided it by the sine of the angle of refraction, he found that he got a constant number. He got the same number all the time, provided we're talking about the same pair of media. If you're talking about air to water or water to glass or whatever. So that is for a given pair of media. That relationship always works out to be the same number. Whatever that number is depends on what the pair of media is. But that's his law. So it's a very important law. So have a look at it again in our notes. And what we're saying is Snell's law. Well, if they ask you Snell's law, you can write it down as a formula if you want. Sine I over sine R is equal to constant. Or if you want to express that in words, it is the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. And there's the part I'm talking about for a given pair of media. That's important. Now, that's Snell's law. So if they ask you Snell's law, that's the definition. But if they asked you to define the laws of refraction, well, you've got to give two parts to it. The first part is Snell's law, and the second part is, well, we have this before when we did mirrors. It says the incident wave, the refracted wave, and the normal at the point of incidence all lie in the same plane. What it means is this. If the incident wave comes in along the screen of the board, then the refracted wave will also move out along the plane of the board. It won't jump out from the screen or into the screen. So they all lie in the same plane. The most important part is Snell's law, but to get full marks for the laws of refraction, you have to mention that second one as well. Right, let's go back to my analysis. So, sine I over sine R is a constant. Well, Snell also found that that constant is also equal to the ratio of the speeds. V1, the speed in medium 1, divided by V2. So that's an extra part to my formula. Now, you know what the wave equation is about? We did the wave equation in a very early lesson. The wave equation is V is equal to F lambda. In the table book, remember, it's written down as C is equal to F lambda, but I prefer V because V stands for the velocity of any wave, a water wave, a sound wave, a light wave. For a C, I think is more for a light wave because C is the speed of light constant. So that's the way I'll use it, mostly, in all our lessons. Well, going back here, V1 is F by lambda 1. Notice I don't put down F1 because F does not change. I just said that. F depends on the oscillator. So F is the same in both media. And what's V2? Well, it's F lambda 2. And what happens here is that the F's cancel. Now you end up with this triple part formula. You have sine I over sine R is equal to V1 over V2 is equal to lambda 1 over lambda 2. Now I want you to learn that formula. Is that formula in the table book? Parts of it are, but it's not written like that. And I like it like that. So I want you to learn that formula there. That's using Snell's law for all kinds of waves, sound waves, water waves, you name it, any kind of wave you want. Now we're going to solve certain problems, and I've got a problem solving technique. Some of these problems can be a little bit tricky, so I'm just going to give you a nice technique that will solve any problem very easily for you in refraction. So draw a table. You're talking about a wave moving from one medium into another medium. Let's call the top part here medium 1. And the second part here medium 2. This is a 3-part formula, but you'll only need 2 parts in most problems. So the first part involves the angles. So they might give you I and they might give you or ask you to find or. The second part involves the speeds. So that's the speed of medium 1 and the speed of medium 2. And the third part are the wavelengths, lambda 1 and lambda 2. So lay your information out in the table, apply that formula, and you'll see that these problems are going to be very, very easy. So let's have a look at 2 examples. Using this formula, sine I over sine R is V1 over V2 equals lambda 1 over lambda 2. 3-part formula. You'll just need 2 parts to use in most problems. Set everything out in a table as such. So let's have a look at example 1. Sound waves are incident from water to air. Check the order. Water goes first, then air. At 30 degrees, that's the angle of incidence in the first medium. We want to find the angle of refraction, or. There's 2 constants we're given. We're given the speed of sound in air. We're given the speed of water in air. So we're given speeds. So you know, what are we given? We're given angles, we're given speeds. So I'm going to use the first part of that formula, and I'm going to use the second part. They're the 2 parts that I'm going to use. So let me have a look at this question in detail on the board. Example number 1. Well, sound waves are incident from water to air. So water goes first and then air. Look, you won't get that table in the exam. When you do your exercise later on, you'll have to manufacture that table yourself. But believe me, it's a lovely, simple way to do these questions. What am I given? I'm told the angle of incidence in water, the first medium is 30 degrees. So I is equal to 30 degrees. They're asking me to find the angle of refraction, which is in the air. What constants have they given me? They've given me the speed of sound in air. We'll call that VA. And that value is 340 meters per second. Sorry, put it down here. VA is 340 meters per second. And they've given me the speed of sound in water. And that value is 1,500 meters per second. So there's my table. Now, as I said, I just need the first part and the second part of the formula. So let me write it down. I've got sine I divided by sine R. And that's equal to V1, which is W, VW, divided by the air, VA. So there's my formula. Let me now put the numbers into it. So it's sine I, sine 30 degrees, all over sine R, is equal to VW, 1,500, divided by VA, 340. The kind of maths you need to be able to do for higher level physics is solving something like that. Can you manipulate the formula? And can you find or get or on its own and then use your calculator? A lot of these questions, I'll be doing cross multiplication. So just put in these arrows here in your head. I'm looking for or. Well, first of all, let me get sine or. So I don't want sine or down below the fraction. I want it above. So slide the sine or up to the right. Just follow the arrows. Leave the sine 30 there. Slide the 340 up in front of it. So I've got 340 sine 30. And slide the 1500 down below it, divided by 1500. As I said, I don't want sine or, I want or. So the way you do that is you get the inverse sine of the left-hand side. So let me write the or here. Or is equal to the inverse sine, is written like that, of 340 sine 30 divided by 1500. So I'm going to put that into my calculator. So let's go to my calculator, show you the calculation. So I've got inverse sine, so it'll be shift sine, fraction on top. I've got 340 sine 30 degrees, close bracket, scroll down to the bottom, over 1500, close the outer bracket, and then execute. And I get an answer of, say, 6.5 degrees to 1 decimal place. So my answer for the angle of refraction, or to 1 decimal place, is 6.5 degrees. That's the level of maths you need to do higher level physics. Just be able to manipulate a formula and use your calculator. Let's have a look at example 2. So in example 2, I've got a yellow light of wavelength 5 by 10 to the power of minus 7 meters. It's incident from air to water. So air goes first in your table and then water. They're going to give me the speeds of light in air and the speed of light in water. Well, actually, the speed of light is always the same. It's always 3 by 10 to the power of 8 meters per second. It never changes. But what happens when it goes through something like water? It gets scattered. It gets absorbed and re-emitted by the molecules of water. And that time lag gives you the impression that the light is traveling more slowly. But light never changes speed. You want to find the wavelength of yellow light in water. Now, they can't give you the wavelengths of yellow for every medium it travels through. So, in general, the wavelength of yellow light is given in air or a vacuum. Anyway, let's look at this question in detail on the board. So, it's incident from air to water. So, air goes first, water goes second. What do they give me? They give me the wavelength of yellow light in air. They don't say it's in air, but you've got to assume that. When they give you the wavelength of yellow light, they mean in a vacuum or air. So we'll call that in air. We'll call that the wavelength lambda in air is 5 by 10 to the power of minus 7. They're asking me to find the wavelength in water. They're asking me to find lambda W. And what's the other piece of information they gave you in your question? Well, they gave you the speed of light in air. We'll call that VA. And that's 3 by 10 to the power of 8 meters per second. And they gave me the speed of light in water as 2.25 by 10 to the power of 8 meters per second. So the parts of the formula I'm going to be using here will be this part here, the speeds, and this part here, the lambdas. So write it down. I'm going to write down VA, the top one, over VW. And that's equal to lambda A divided by lambda W. So now let me put the numbers in. VA, that's 3 by 10 to the power of 8, divided by VW, 2.25 by 10 to the power of 8. That's equal to lambda A, 5 by 10 to the power of minus 7, divided by lambda W, which they're asking you to find. So again, let's do some simple manipulation. Do a little bit of cross multiplication. Put the arrows in here in your head and move everything up along the arrows. If it's down, move it across and up. If it's up, move it across and down. I could do a little bit of cancellation here. The 10 to the power of 8s will cancel. So I'm looking for lambda W. So slide the lambda W up to the left. And that's equal to, slide the 2.25 up to the right, where it joins the 5 by 10 to the power of minus 7, divided by, slide the 3 down. So I'm going to put that calculation into my calculator. So let's have a look at that calculation. So what have I got? I've got fraction. I've got 2.25 multiplied by 5 multiplied by scientific notation down here, minus 7. Scroll down to the bottom, divided by 3. Execute. I get this fraction. I want to turn that into a decimal, or in scientific notation, suppress format. Add decimal. Okay, so I get an answer of 3.75 by 10 to the power of minus 7. So my answer is the wavelength of yellow light in water is 3.75 by 10 to the power of minus 7. And look, when you're finished the question, make sure you put down the units. That's essential. You lose marks if you don't put the units in the answer, and that will be meters. Which kind of makes sense. The wavelength gets smaller as it moved into a slower medium. So that tallies nicely. Can I predict which way the wave bends as it passes from one medium to another? I can. So for example, if I have a wave that's traveling from one medium into the other, let's say this medium it's in right now is faster than the one it's moving into, which is slower. Well, when it moves from a faster medium into a slower medium, the wave will bend towards the normal. Like that. And what do I mean by towards the normal? Well, if I look at the angle of incidence, I, and the angle of refraction, or, well, you can see that or is smaller than I. It's a smaller angle, so it bends towards the normal. If, on the other hand, my ray of light goes from a slower medium into a faster medium, what happens to it? It bends away from the normal, like this. So what does that mean? Well, it means that the angle of refraction, or, will be bigger than the angle of incidence. So you can predict which way the wave will bend if you know the relative speeds in each medium. Let's talk about a little bit about speeds in different media. Let's talk about the speed of sound. In 3 media, air, which is a gas, water, a liquid, and steel is a solid. The speed of sound goes up as the material becomes denser, because the way sound is passed on is from molecule to molecule. So the denser the molecules are, the faster the sound will be. So air is 340 meters per second, water is faster at 1500 meters per second, and steel is 5000 meters per second. That's why if you want to hear a train coming, if you put your head to the track, you can hear it coming down the steel before you can hear it through the air. What about light? Light does the opposite. The fastest light can travel is in a vacuum or air, which is 3 by 10 to the power of 8 meters per second. But in water, it slows down to 2.25 by 10 to the power of 8, and in steel, down to 2 by 10 to the power of 8. Now, the speed of light actually never changes. It's just when it goes through water or steel, it interacts with the molecules more, it gets scattered, where it's absorbed and re-emitted, so it has the appearance of slowing down. Let's talk about the refraction of light in particular, rather than just waves. The refraction of light. Well, let's say I've got a ray of light that's shining on the boundary between two media, air and water. That's the incident ray, and of course it makes an angle of incidence to the normal. Can I predict which way it's going to bend? Well, light travels more slowly in water, so it's going to bend towards the normal. There's my refracted ray. My angle of refraction will be smaller than my angle of incidence. So we have Snell's law, of course, don't we? That says that sine I over sine R is equal to a constant number. Well, that constant number, when it comes to light shining from one medium into another, is called the refractive index. And the refractive index I'm going to denote by the letter N. So N stands for something called the refractive index. Now that refractive index is from one medium into another medium. It's from air, A, to water, W. But when I say the refractive index of water, the refractive index of water, which I call NW, it actually has a value of 1.3. That's the constant number for sine I over sine R. Well, I've left the A out. The A is assumed. So it's going from a vacuum or air into water. You can put the A in if you want, but it's assumed. When I say the refractive index of glass, when I say Ng, its value is actually 1.5. I mean going from air into glass. The air is assumed. The refractive index for diamond, these are all in your notes if you have a look at it, is 2.4. I mean from air to diamond. So when we say the refractive index of a material, we're assuming it's coming from air. The higher the number for the refractive index, the more the light is going to slow down when it enters that medium, and the more it's going to bend. So you can tell from the refractive index how much the light bends. The refractive index of air, what do you think that value would be? Well, we're talking about going from air to air. So you're not really going from one medium to another. You're staying in the same medium. So the light's not going to bend. So the refractive index of air is 1. So remember that value. Sine I over sine R. I and R will be the same because the light doesn't bend. So the value is 1. Let's talk about the problem-solving techniques for refractive indices. So here I have a ray of light going from medium 1 into medium 2. There's the incident ray, there's the refracted ray. The incident ray makes an angle of incidence to the normal, and the refracted ray, the angle of refraction. In my table, we may be given values for I and R. So I is in medium 1 and R is in medium 2. You may also be given the speed of light in each medium. So the speed of light there is called V1 and the speed of light in medium 2 is called V2. So you may be given V1 and V2. You may be given the wavelengths. The wavelengths are lambda 1 and lambda 2. Now, a fourth thing you may be given, which we haven't done yet, you may be given the refractive indices of the materials. You may be given the refractive index of medium 1. I'll call that N1, but it means going from air into medium 1. And I may be given the refractive index of medium 2. There are 4 possibilities, 4 things you may be given. There's only 2 that you actually need to solve a problem. Here is my expanded formula now for problems involving refraction of light. We have sine I over sine R is equal to V1 over V2. is equal to lambda 1 over lambda 2. So we've already seen those three parts, and now we're just going to add on a fourth part, the refractive indices, but you've got to be careful here. You've got to turn these upside down. It's equal to n2 first over n1. Why is that? It's just the way that we measure refractive indices. Don't worry about it. But that's now my expanded formula. That formula now will take care of all my refraction problems. Everything is in there. Table plus formula. Is that in the table book? Well, parts of it are in the table book. If I actually have a look in my table book, page 60, I can see the refractive index n is equal to sine I over sine r. So that part of it is there. There's another part which we'll talk about later in the next part, or the next third part of this lesson. So let's have a look at some examples. Example number 3. We're told that light is incident from air to glass. So air goes first in your table, followed by glass, and the angle of incidence is in the air, and that'll be 30 degrees. We have to find the angle of refraction. What other information are we given? We're told that the refractive index of glass is 1.5. Okay, so let's have a look at this problem here. So light is incident from air to glass, so air first, then glass. The angle of incidence is in the air, and that's 30 degrees. So I is 30 degrees. And the angle of refraction, that's R, in the glass. We need to find that. What information am I given? I'm told that the refractive index of glass, Ng, is 1.5. What's the refractive index of air? Well, I'll know that already. That's 1, because we're going from air to air, so the light doesn't bend at all, so that's 1. So there's my information. It's a 4-part formula. I just need 2 parts. I'm going to use this part here, and I'm going to use this part here, but be very careful. We're going to make sure that the refractive indices are turned around. They're the wrong way around. So be careful with that. So I've got sine I over sine r. That's equal to, I'm not going to say Na divided by Ng. I turn them around to Ng divided by Na. So you see in my formula they are reversed. So let me put my numbers in. Sine 30 over sine r is equal to Ng, which is 1.5, divided by Na, which is 1. I want to manipulate that formula, so you can do it by cross multiplying. In your head, put in these arrows. Let's bring the sine r up to the right hand side. It's down, so bring it across and up. So I have sine r here. Bring the 1 up, which makes no difference, and the 1.5 down. So it's sine 30 divided by 1.5. I want r. R will be the inverse sine of the left-hand side, which is sine 30 divided by 1.5. So let me put that into my calculator. So I've got inverse sine is shift, sine, fraction. On top I've got sine 30. Close the bracket. Scroll down. On the bottom I've got 1.5. Close the bracket. Execute. I get an answer of 19.47, or let's say 19.5 to 1 decimal place. So my angle of refraction is 19.5 degrees. But this is a nice technique. It'll work for all kinds of problems. Let's have a look at the next example. So let's go on to example number 4. So it says light is incident from water to air at 10 degrees. So water will go first in your table, followed by air. We've got to find the angle of refraction or. The information they give me is the refractive index of water is 1.3. So let me look at this in detail on the board. So I'm going from water to air. So water is first in the table, then air. And the angle of incidence, which is in the water, will be 10 degrees. They're asking me to find the angle of refraction. They've given me the refractive index of water. The refractive index of water, NW, is 1.3. And you automatically know the refractive index of air, that's 1. So you're going to apply your formula. You just need the first part of your formula involving the angles and the last part of your formula involving the refractive indices. But don't forget to turn them upside down. So it's sine I over sine R is equal to, turn them upside down, NA divided by NW. So let me put my numbers in. Sine I is sine 10 degrees, all over sine R, and that's equal to NA, which is 1, over NW, which is 1.3. Cross multiply as usual. So I want to isolate the sine R and then the R. So sine R is equal to, slide the 1.3 up to the sine 10. That's 1.3 sine 10 degrees. Therefore, R will be the inverse sine of that. The inverse sine of 1.3 sine 10 degrees. So let me go to the calculator and put that in. So I've got shift sine, that's inverse sine, and inside the bracket I'm going to put in 1.3 sine 10 degrees, close the bracket, and close the bracket again, execute, and I get about 13.05 degrees. So my angle of refraction is about 13.05 degrees. Moving on to example number 5. Light is incident from water to glass at 15 degrees. Water goes first, followed by glass. The angle of incidence of 15 degrees is in the water. Find the angle of refraction. What do they give me? They tell me the refractive index of water is 1.3 and the refractive index of glass is 1.5. Right, so let's have a look at this question in detail. So it's going from water to glass. So water first, followed by glass. The angle of incidence is in the water, and that is 15 degrees. They're asking me to find the angle of refraction in the glass, or the information they've given me is the refractive index of water, NW, is 1.3, and the refractive index of glass, NG, is 1.5. So I'm going to use 2 parts of my 4-part formula. I'm going to use this part here involving the angles and the last part involving the refractive indices. But remember to always turn them upside down. So I've got sine I over sine R is equal to, turn them upside down, it's going to be NG divided by NW. So let me fill the numbers in. Sine I is sine 15 divided by sine R is equal to NG 1.5 divided by NW 1.3. So I want to solve that for R. So let me do the cross multiplication in my head. Put the arrows in your head. I want to isolate the sine R. And that's equal to, slide the 1.3 up, 1.3 sine 15 degrees, and slide the 1.5 down, divided by 1.5. Or will be the inverse sine of the left-hand side. So it's the inverse sine of 1.3 sine 15 divided by 1.5. So I'm going to put that calculation into my calculator. Shift sign, that gives me inverse sine, fraction button, 1.3, sine 15, close bracket, scroll down to the bottom, 1.5 is on the bottom, close the outer bracket, and that executes to 12.96, which is about, say, 13 degrees. So the answer for the angle of refraction is approximately 13 degrees. Let's move on to example number 2. Or sorry, example number 6, should I say. So example number 6. I've got light is incident from air to a medium. We don't know what the medium is. So air goes first, the medium goes second. And the angle of incidence in the air is 30 degrees. If the angle of refraction is 20 degrees, we want to find the refractive index of the medium. So let's have a look at this in more detail on the board. So light is incident from air to a medium. So air goes first, followed by the medium, and the angle of incidence in air is 30 degrees. Here, they also give me the angle of refraction. The angle of refraction in the medium or is 20 degrees. And what they're asking me to do here is to find the refractive index of the medium. So we're talking about NM equals question mark. We know what the refractive index of air is, don't we? The refractive index in air is 1. So I'm going to take two parts of my formula. I'm going to take this part here, and I'm going to take the last part. So write it down, sine I over sine or is equal to, but don't forget, of course, to turn the refractive indices upside down. It's going to be NM divided by NA. So let me put the numbers in. Sine I is sine 30. Divided by sine or is sine 20. And that's equal to NM. I'm looking for that. Divided by NA, well, that's 1. So I can just forget about that. So the refractive index of the medium is simply sine 30 divided by sine 20. So let me put that into my calculator. So fraction button, sine 30, close bracket, divided by sine 20, close bracket, execute. And I get about 1.46 is the refractive index of the medium. Okay, so that's more or less it in terms of all the difficult calculations. What else do you have to do in this part of the lesson? Well, you need to know a demonstration of refraction. It's very simple. Read through it yourself. Make sure in the exam you put down your 3 headings: apparatus, method, and observation, as well as a diagram. What about applications of refraction? We've got totally reflecting prisms and we've got mirages. So I want you just to read through those, familiarize yourself with them. Just read is all I'm saying. There's no need to actually learn them in any great detail. And now it's over to you in terms of doing the exercises or problems before you move on to the next part of the lesson. So if I scroll down here to the exercises, you've got lots of questions. You've got refraction of waves in general, 1 to 6. And then you've got refraction of light involving refractive index, going down to number 13. You've got about 13 questions to do. Get them done, and then you'll be ready to move on to the next lesson.